Now, previously I talked about derivatives as limits or the instantaneous rates of change of a certain graph as limits. So for example, if I wanted the instantaneous rate of change of x squared, I have to write it as a limit as x approaches, or sorry, as h approaches 0 of f at x plus h minus f at x over h. Now, this is a very tedious process, right? Like, let's say I wanted x to the 3, or let's say I wanted x to the 7, that just would not work. So instead, there are these things called derivatives, which is kind of like a formula or an operation you take on a function, which will give you the instantaneous rates of change. So, for example, let's say I had x to the n. If I want the instantaneous rate of change of f at x equals to f to the n, we say f prime at x would equal to n times x to n minus 1. And we call this differentiation, right? And it can also be a different notation. We could say the d of dx of x to the n would equal to n times x to the n minus 1. And personally, these are the same. However, this one you'll see used a lot more in higher levels simply because it tells you what function you're differentiating, so x to the n, and it tells you in terms of what variable. And when you kind of do more than one variable, more than two variables, this becomes very helpful. And you could also use it in chain rule and higher order derivatives. Now, there are other properties of derivatives. For example, let's say I had the d of dx of c times x to the n. You could just bring this constant out. So this would just equal to c times the derivative of x to the n, which would equal to c times the derivative, or sorry, c times n to the x times n minus 1. Now there is also another property, we call this the addition rule or the addition property, and that is if you were to take the derivative of two different functions added together, let's say f at x plus g at x, this would equal to the derivative of its separate terms, like so. And today I'm just going to go through some examples using this rule, the constant rule, and the power rule, which is that. So, for example, um, find f prime at x if f at x equals to x cubed. Now we know from the formula that f prime at x of, or sorry, if f at x equals to x to the n, then f prime at x equals to n times x to the n minus 1. So if we have f at x equals to x cubed, f prime at x would equal to 3n times x to the 3 minus 1 would equal to 3x squared, like so. Now let me do some other examples involving a radical. Let's say find d of dx of y if y equals to the square root of x. Now, right away, you can see that this isn't a power, right? This isn't a power function. However, I could write it as a power function. I could say y equals to x to the 1/2. And in this case, we would just apply the same rule. So we would just say y equals to, we bring the power down, 1 over 2 times x to the 1 over 2 minus 1. This would equal to y, or sorry, the d of dx. Very important. Would equal to 1 over 2 times x to the negative 1/2. And then the d of dx of y would equal to 1 over 2 root x. And whenever you say the derivative of y or d of dx of y, you're actually saying the derivative of the function y in terms of x. So let's do a different problem. Let's say I said find the u over dt if u is equal to t 4t squared. Now, we want to find the derivative of u in terms of t, so let's do that. And we know from the constant rule, if we want to find du over dt, this would equal to 4 times the d of dt of t squared. And at this point, we could just apply the power rule here, which would equal to 4 times 2 times t to the 2 minus 1, which would equal to 8t. Now let's try something a little bit different. Let's say I had the function f at x equals to 4x to the 7 plus 2. What happens here? Well, we would say derivative in terms of x of f at x would equal to, we would bring the power out here, right? So it'll be 4 times 7 times x to the 7 minus 1. And then we could say plus 2, or plus the derivative of 2. We are not sure what this is yet. However, I can write this 2 as, I can instead write it 2, I could write 2x to the power of 0, right? Because x to the power of 0 is just 1, and 2 times 1 is still 2. So this becomes 28x to the power of 6 plus, we drag the power down here, 2 times 0 times x to the negative 1. And anything times 0 is just 0, so the d of dx of x f at x equals to 28x6 plus 0. And this actually works for all constants, no matter if it was pi, if I want to take the derivative of pi, the derivative of the square root of 3, the derivative of 10 to the 9, a billion, it wouldn't matter. It would just all equal to 0. And you can kind of think of it as a vertical translation of my graph will not change my instantaneous rate of change at a certain point. So, to kind of sum it up, we learned that the derivative of x to the n would equal to n times x to the n minus 1. We learned that the derivative of any constant c would equal to 0. We learned that the derivative of c times any function f at x would equal to c times derivative of f at x, like so. And we learned that the derivative of f at x plus or minus the derivative of g at x would equal to the derivatives of each part. And that's it. I hope you learned something, and make sure to come back.